About a week ago, I did a video introducing my 6497 watch movement. It's one of these very commonly shown CAD models. That's for good reason. It's really nice. Anyway, I've got an Onshape version of it that I showed last week, and it kind of looks a little bit like this one here. But it got me thinking, and I had a few days spare noodling on it, and I have come up with a new approach. Now, it's not finished yet, as you'll see, but I've been test driving a lot of techniques that I really think that need to be highlighted more. The one that's in the public domain from another CAD system is great, and it's been a perfect reference, and I'm much indebted to it. But it really isn't particularly accurate in some ways, and also it's not parametrically driven. The individual parts are, and the assembly is just the parts of, from a bottom-up approach. And so what that really is that often what happens is that you can draw things in CAD, but can you design them, right? And that's a different story. So I'm trying to have an approach here where I really, examine how I would design this thing, not just draw it. I know that I can draw it. Anyway, so, so far it exhibits the same properties as before. The animations work, and everything, for the drive, for the going train is working. And let's dig into a little bit of some of those techniques that I'm talking about without showing it yet. So this is not so much a demo as an exploration, and it isn't complete, so I'll probably have to do another follow-up when I do finish this thing off, because I think it'd be worthwhile in the end. Right, so I'm using a bunch of different techniques, including top-down techniques, layout techniques, in context, and all sorts of things. And not one particular technique is correct. In fact, I'm going to use all of them at different times. What I have done at the beginning here is create a variable studio, and a variable studio is its own tab here, which has got the key dimensions like the outside diameters and a few lengths and depths and offsets that really mark some of the design. Now here already is a bit of a problem, because a lot of this is already designed in, and even though I've captured them here, the reason that this is say 0.24 or 0.28 or 0.16, those decisions were made a long time ago for, say, the diameter of this axle, and so I'm not kind of rethinking any of that. But I want to see how these flow through in the rest of the model. So given these, and I can come back and add more of these variables in as I think, and I want to put them here at the top rather than burying them in any sketches or burying them in any particular parts. So I've got this part studio here called the main layout, right? And so the main layout, if I just go to the top view here and turn off the planes, this is the layout of the drivetrain, of the holes, of where the dial feet will go. This is where the barrel will go, and this is where the balance goes over here. So I've actually separated them into different sketches. Like the base profile is the outer diameter and this little offset. The pivots here, these are the where the setting wheels and the power delivery, these are the pivots for those sorts of parts of the mechanism. So it's laid out functionally. The main one really is the train of wheels here. All right. And I've played around with some extra local variables here, but the beauty of the variable studio is that the variables that are defined globally will be available to me here. So any of these diameters or lengths or offsets will, I just refer to this variable name, and it will be, so you can see here, in the train of wheels, yes, there's a lot of diameters, but then in fact that's being driven by this second wheel pinion, or second wheel outer diameter here, which is 9 millimeters. So, I'm not really doing anything specific in this sketch, other than just creating the entities that I'm going to be able to refer to later on, and all these holes as well. This is the final sketch. So I've got a bunch of sketches, it's 8 or 9 of them there, and I'm going to start with that and then flow them into a series of part studios. Now, the point of doing this is that I don't have to redefine or double up or make things stomp on each other's toes by creating this as a global thing. I've created, and this is one of the first, one of the real decision points, is like, how many part studios do you use? And when do you split from one part studio and start another one? Or do you do it all in one? Or do you do all parts in separate part studios, which is more like the old traditional way of doing things in CAD, where, one part, one file type of thing. So I'm not doing it that way. I am doing it with a more modern multi-body and multi-part part studio approach. And you'll see here that this, I'm keeping things reasonable. There's 100 features in here. There's nothing. It's a tiny part studio, but it generates 10 different parts. It generates the main plate, which is that big machined out piece here. It's like the main backbone of the watch movement. And then there's a whole bunch of little things like these jewels. Now, these jewels are so tightly parametrically linked to the main plate, is that it makes sense to add a few features and create them here. And then there's a little bit of a twist to it as well. So let's start at the beginning. I'm going to roll back and show you. First thing I did is I used a derive feature. Now, a derive feature here lets you to choose something from another part studio, i.e. the layout sketches, or indeed another document, right? And bring them in and derive them into this part studio. Now you can see it's all done in one feature, and I can edit it, and you can see the ones that I actually, I chose all of the things in the main layout. So all of these things came in, right? So now once I had that, I could start to build some features into this part studio. So the first thing I did was, I just used those edges and those faces created from the sketch and started creating, the main guts of the outline here. Now, I did create some additional sketches inside here, and this is for where the setting stem is going to plug through here, and I need to create some clearance. And those things are not defined at the global level, because they don't affect anything else other than this local piece of the part here. So I did everything like that locally here. And you can see there's a bunch more features. I'm cutting out these things. This is on the top of the plate. This is where the setting mechanisms go, and some of the winding power, and this is where the second wheel goes here. So the minute wheel goes. Anyway, so those features sort of lead me up to, that's the top of it, what I called the top. What I should do? I call the top. And then there's a whole, I've put everything in folders as well. So these are feature folders. There's a hierarchy. There's no hierarchy in terms of referencing. It's just a feature folder. So now I'm doing these other cutouts. I just put things in the wrong way there. Oops, I'm going to just do it this way. So if I roll to here, you can start to see I'm doing the other cuts that belong to the bottom of the board here. So of the board of the mechanism. If I show you this one here, this extrude. Now this extrude here, you'll see the height or the depth of it, goes from this reference plane here all the way down 1.65 millimeters. Now that was actually a variable, which you can see now. I can expand the width, and you can see the variable name here. This was one of these top level variables that I defined at the sort of global level. So this is nice because if the design changes, then there's a whole bunch of things that are going to be referencing that same height. Right, this is the problem I had from, looking at other models that are in the public domain, is that everything is sort of individually set. There's no link in between, the height of where the balance is, the height of where the escape, the pallet fork is, and the height where the second and third wheels go. So because of that, that was really where I had the most problem with, not just following how it was designed, but accepting that this was, a good teaching instrument. Anyway, so I have, a few more features. Now this is where the bulk of the fiddly features are. I mean, you can see we're already up to 40, extrude number 42, and this is a lot of, there's a lot of individual things in here. And of course I'm using, referencing everything from this layout. I can turn the layout off to make it a little bit clearer of where we're at. So that is the most cutouts, and then I did a whole series of holes, and I used the hole feature extensively just because it is quite convenient. It will actually give me a good whole table, collating all of the 1.2 through holes, the ones that have got the 0.9 holes that have got the countersink, the counter bore here. You can see here, the whole tables are, and obviously this will come out in the drawing as well. So I used those. Now, of course, variables are at play in here as well. So, the definition of some of these key holes, and those key holes that I'm talking about here would be something like, what would be one? Maybe where there's a big sort of shock bearing jewel here called the Inca block, right? And it's a special bought-in thing, so I'm not going to locally specify the sketch for it. I'm going to just use the dimension that I referenced from the top level. So I got my holes now, and then I just did some a quick engraving down here. Just for the, I'll put put the actual manufacturer's logo here later on, but not for YouTube. And then, so that is the end of the main plate, and you can see I've created one part in it automatically. I've created one part. Now, if I go on further here, and I roll down, I've actually created an additional 1, 2, 3, 4, 5 jewels. So these are the jewels that go into the plate here. Now, again, because these are so parametrically linked, it makes sense to do these as part of the part studio. They're also very, very simple. You can see here one of the sketches for it. It's a simple revolve, and here's the profile for that, which I'm going to revolve around the center line. Of course, that's being referenced from this hole here. Now, the one dimension I want to call out here is this 0.02. Just an aside, these are very small dimensions, and they're real. Now, these are millimeters, so that's 20 microns. Pretty small in any one stretch. But this is a very key one here because it is the offset from the flush plane here. Right. Now, this maybe it was going to be easier to show it in the assembly a little bit later on. Okay, for now, just remember that there's you can see here, there's a parallel distance between these two of 0.02 millimeters, and I'll explain why that needs to be variable later on. So it's the same thing going on over here and here as well. So each of these jewels has a little bit of an allowance or a variation built in there. So next thing. So I've got these parts, and I guess what a lot of people in traditional CAD would do is that you take all these parts into an assembly and maybe create a sub-assembly. Or, if you're really lazy, you would just go to a top-level assembly and just keep putting the parts in, and that would be one way to do it. Now, I've used a composite part. This composite part feature comes next, and I'll show you what that is. What this does is it collects up these parts that I've chosen, the jewels and the main plate. And I'm not going to tick this box here. Closed, if I tick the box on closed, it would take away all of these parts, so I could never kind of individually do detailed drawings of them, or maybe insert them in other things later on. So what I have done is create one composite part in addition to these parts, and I've called it the main plate jeweled. Now, the reason I've done that is how it is called out in the bill of materials, in the official manufacturer's data sheet and spec sheet. So you have a jeweled main plate. That is how you purchase it. All right, so that's how. So the composite part's really, really good for that, because I'm going to be able to use it later on just as a part, a single part. It will appear in the bill of materials as a single line item, main plate jeweled, and I don't have to worry about things because it is a parametric feature here, and if I change any of these other features, then of course the composite part will update as well. Now, I've done the same thing in a number of other parts, and let me move to that quickly. So I will go to the subassemblies now and show you the old method of doing things was to, as I said, bring the main plate in and bring in all sorts of individual parts, maybe group them together, or maybe do lots and lots of fastener mates. Those things just take up more time and take up, it's unnecessary, right? So what I have done is, and if I go to the top level assembly, you'll see that I have just inserted the, we call that the main plate jeweled. Okay, so I'm showing some red here, and that is because I have rolled back. I need to roll to the end. So I did a couple more parts in here. The parts that I chose to do in this part studio were ones that were very, very tightly linked parametrically and geometrically to this whole what I'm looking at here. Now, you could argue that absolutely everything is linked geometrically because it all does fit together in one way or another. That is going to be the art and science of deciding how many of these part studios you do have versus throwing it all into one and having some very, very long regeneration in that time. So I'll leave some of that to the reader to decide, and the rest of it, we have lots and lots of help on this type of thing on the Onshape Learning Center. Anyway, so with this part studio now in a good state, I can go back to the assembly, and you'll see in the assembly the first thing I put was this, indeed, a composite part called main plate jeweled. All right, and then I just, I can quickly show the bill of materials here. And let's add a column for name, bring that over to the left. We don't have any part numbers right now, so I'm just going to remove that. So you see main plate jewel is just a quantity of one. And I've done the same thing for the pallet bridge and also the train wheel bridge, because again, these things are available in the bill of materials of the manufacturer as a sort of item like this, as a single item, including the jewels. All right. So while we're here, a little interesting side note. If I take a cross-section through one of these, any one of these, like this, it's a really cool trick as well, as you can do a multiple, you can have two cross-sections like this, and as long as you choose the correct side of them, you can create these nice pizza slices or pie slices, so that you can see a couple of things all at the same time. So we can see these axles. Now these are different colors, like this orange, the gray, and the light gray. In fact, that is another composite part that we'll talk about in a minute. But this is it's a bit of a tangent, but the way that these things work. Right, there's these red things here are jewels, and the jewels operate as a really, really, really hard bearing surface, as close to frictionless as they can get, as they possibly get. And there's a tiny amount of lubrication is placed on this when it's assembled. Anyway, so this thing, there's a slight clearance in here. You can't bind it up, but you have to have a little bit of clearance. Likewise, the length of it doesn't quite touch between, if we measure this, if we measure the, from here to here in this section, it's 0.02. Remember that number. This is the exact number that that a little allowance that I had put into when I was creating these jewels. Now that is going to allow what they call endshake, so the vertical travel that is allowable for this axle, or for this sort of wheel, kind of little subassembly of the wheel and the axle and the pinion that's on it. Right, so the endshake is really, really important, because if you don't have enough endshake, it will bind and stop working. If you have too much endshake, it'll get sloppy and things will come out of mesh, and also will bind and it will stop working. So you've got to have the endshake right, and between 0.3, 0.4, or 0.03, 0.04, 0.05 millimeters is desirable. So just for the purposes of today, I've created a top-level variable called endshake adjustment, and I've set that at 0.02. Now this is on each end, so I've got 0.04, and I can change that, and this, the whole thing will update on that as well. So it's the equivalent of you coming in, or the watchmaker coming in and pushing this jewel down, up or down, to facilitate the endshake. Now you can do it as simply as going to your variable table and playing with that number. A lot simpler, easier said than done in physical life sometimes, but that's the beauty of CAD, I guess. Right, so where were we? So that was the endshake, and from a variable showing you some of this first part studio, which was the major parts that are going in here. The next part, the ones that probably are really interesting, are these wheels. Right? So there's this wheel train, or the going train, that is how you get from how you transmit the motion. The motion works is another name for that. Right. So I used the sketches again. I derived that from the layouts. You can see here, so that I could position the axles, I could position the upper and lower bearing surfaces of those axles again, because that was driven by these setbacks from the global variables. So I created initially just these smooth discs like this, or smooth gear wheels and smooth pinion sort of cylinders, so that I could get the thing laid out correctly. Then I came in and did something at the end to create the gear teeth and the pinion leaves. Like, there's actually a different in nomenclature here. This is the pinion, and these are called leaves. This is the gear, and this is called the tooth. Now, the other interesting thing is that watchmakers and watch clocks they use a different sort of gear shape. All right, it's called a cycloid gear. Now, you can search all that up, and why cycloid gears are necessary, why they're very low friction. And there's actually a standard for them as well. So the BS 978 is the British standard for gears for instruments and clockwork mechanisms. So it's cycloidal type gears. So really interesting thing. You may not want to pay $150, but just believe me, if you're into this, then you would be definitely paying for something like this. So what I did do is I built based on the information that's available on that standard, a custom feature that creates these cycloid gear pairs. And based on what I want to do is based on the number of teeth on the wheel and number of leaves on the pinion, and the module, it will create this pair. Right? So then I'm going to use this as a template to adjust and cut out the so that's what I did. And I used another custom feature called Super Derive, which is a very fancy and form of derive, which allows me to derive and then translate exactly the sketch that I wanted. So I brought in sketches from over here, and you can see then, I laid that sketch exactly at the middle of this disc, and then did a single extrude feature to extrude and cut the teeth out. Now that was all very nice. Now I have done all of those parametrically in here, you can see here the third to center wheel is actually going to regenerate that. Now the regeneration of that cycloidal gear pair takes about 3 seconds or so. I think it says, yeah, oh no, it's not even that. It's 1.37 seconds to do the this whole sort of feature here. And there's 2 of them on top of each other, just so that I translated it so that I could easily do this. There's the pinion leaves, and there's the gear wheel teeth. So I have put this in the same document here, but would be better is if I took this outside, moved it to its own document, and then when I use it, which is in this part here in the wheel train, I would then just use a version reference to that outside document. Here, what is happening is that when I use this super derive, and then I'm actually going to have to regenerate these things each time. So I'm adding to the regeneration time in here. You can see here super derive 5, 6, 2, 4. These are, well, number 5 took the longest, but the other ones, because it needed to be fully regenerated there for some reason, I changed some numbers. So it would be better if these external things that really aren't going to change, because to be honest, they're never really going to change. Once we've fixed, well, the gear ratios are fixed, it has to be, that 60 minutes does equal an hour, and it's going to continue to equal an hour. So, those ratios aren't going to change. Maybe we're going to change the module a little bit, so we'd want to fiddle with that. But again, this is something that's been kind of set in stone for many, 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 many years. So it makes sense to pull these out into their own document and then refer to them using a version reference, and then you'll see here. Now, the next bit was the motion. The motion works have to go into motion. So I created a subassembly called the going train, where I brought these things together. And again, the heights of them and the positions of them was driven by key dimensions that were coming from either the layout. So again, I've kept using this layout. Again, you can see here it is. The train of wheels, this is the same layout that's been, sort of threading its way into everything for references. So, if I do change a center position or the position of one of the wheels in some way, then, all of this is going to be parametrically linked. Now, I did also, you see here, if you notice, these are composite features as well. So the escape wheel consisted of the axle, which is the light gray thing, the pinion, which is the light blue thing, and then the orange, right? So those 3 parts are actually how this thing is manufactured, and it's pressed together. However, when you buy it, you buy the single item, right? So this is the single item with the single SKU or part number that is available from suppliers. Same thing with the second wheel, the third wheel, the center wheel, right? So these things are designed and manufactured in separate pieces, but they come together in one and are sold as one. So that is why I've used, and it looks really, really efficient in this bill of materials as well. So the bill of materials for the going train only consists of these four things. Again, I need to put the names in. But I could, if I wanted to, I could create a separate drawing sheet and just detail out the individual part of it, like the pinion, but that's not actually going to be helpful for people going to assemble this or service it or anything else like that. All right, so those go in, and I've got revolutes. Now these revolutes contain an offset from this original. You can see the layout sketch is really at the origin, at the Z0 origin, but this wheel has its bearing surface 1.65 millimeters up from that. Now again, this is being driven by a variable, so it's not going to ever be wrong. The same with these other ones. Variable, top-down driven, layout driven, with composite parts really has been the answer here to create a really efficient, compact, easy to diagnose subassembly here like this. Now, the thing that you've probably all been waiting to see is the animations, right? So I'll turn off that. I have 3 gear relations. Gear relations are up here. I don't need a rack and pinion or screw or linear relationship. This is just purely gear relations. So that allows, this beautiful meshing, and this travels. It's a clock. It's a clockwise. It's a joke. It will, and because these gear ratios are based on the number of teeth, and these things that were designed as pairs, so they've got their pitch circle diameters perfectly created according to the standard, they will mesh nicely like this. And so, even though it is completely, at this point, eye candy, but it's nice. It's nice to see nonetheless. And you don't want to see interferences here or things going at the wrong speed or we're still in the wrong direction. That's the same for all of these other gear pairs as well. So this dark blue light is pushing on the light blue there. And you can see the cycloid action is interesting. You see where it starts to come into contact around about here. It slides over and then comes out just as the next one's going in. So it's slightly different than a regular involute gear tooth. So this is that's the mechanism there. I'm just animating the orange thing manually just with my mouse. See, this is what essentially is the seconds hand, and that is pushing what becomes the minute hand up here. Right. So I'll do that 60 times. That'll go around once. Anyway, that is the okay. Well, one other one that's interesting, only just from a mechanical design point of view, is this thing called the Inca block. It's a suspension mechanism for the jewels in here, and this is extremely fun piece of work here. This is 0.075 millimeters thick. It's kind of hard to believe, but anyway, that's so it flexes, gives you a bit of an end suspension, and because one of the most important pieces of the timekeeping is underneath here, which is the balance, which goes, it's the thing that ticks and tocks, goes back and forward on a very, very fine spring, so it needs help. All right. So once we have that all built in, we've got one above and we've got a similar but different one underneath. You can see here I'm using another section. There's the two. They're called Inca blocks, right? So I created a composite part for both of those because these are sold as units again. You can see the common theme coming in here. Right, so I know I'm going on and on and on, but there's so much in this. It kind of reminds me of my violin model that when you get into it, there's so much I really want to share. So I hope this is indeed interesting. Now, this is where I've got to at the moment. So I've been proving out different approaches, the top-down, the layout, the compositing, driving the assembly constraints from these variables as well. The next thing I'm going to use is some in-context modeling, right? So there's some really critical things that are going to go on with the balance, which goes in here, right? And the pallet fork, which is the thing that we haven't designed that yet. But the balance is going to be really critical, which is the hairspring that goes around, back and forward, back and forward, back and forward. In-context modeling is going to be important here, so I'll use that just as a bit of a demonstration a bit later on. And one last thing is configuration. So I'm using a bit of a mixed bag or digging into all of the possible modeling techniques here. Because not just one thing is not good for everything. The last one is configurations, and this particular mechanism, if you know, the 6497 was designed originally as a pocket watch, which shows the dial this way and the stem comes out the top. Now it's designed to be put in your pocket this way. But it has become popular over a number of years to be worn on a wrist. So you want the stem not at the top, but you want it on the side, usually at the 3 o'clock position. Now, in order to facilitate that, I created a configuration of this dial. Now, the dial is its own part studio, which I separated out. Again, it is kind of intimately linked to the rest of the model, especially with these locating lugs. But, you guessed it, there's top-down design, there's involved here as well. But was also designed, what I did is made a configuration of this where I rotated the references for the sketches 90 degrees so that if I wanted to switch to the wristwatch version of it, what is considered top is now 90 degrees this way, so that the stem will come out at 3 o'clock, and I don't have a 9 and I do have a 6, whereas with the pocket watch I don't have a 6 but I do have a 9 and the stem comes out the top, because these lugs aren't moving, right? These lugs are the important things that keep it indexed against the main plate. Right. So that's a really cool little technique there, because you'll see here that the reference angle, when we look at the sketch plane that I created, I didn't just click the first flat thing that was in front of my face, like this would be the obvious one. The next obvious one that I also didn't click on was the top plane. Right? What I did do is I created a mate connector. Now the mate connector is a really, really handy way to do this type of, because it defines a plane, but importantly it also defines a direction for the plane. So if I dig into it, you'll see that this angle, rotation about Z, is something I can control, and I could set that as a variable. And I've done that a couple of times, especially with the text markings. All right, so if we look down here, the text markings, now these are all just using one of the nice new fonts that we talked about last time. Again, I used the mate connector for the reference. And if I dig into here, you'll see that this is a reference angle variable here, which I've configured. So it's not only a variable, which is here, it's a local variable, it's a configured local variable here. So in the wristwatch edition, I'm setting it to 90. In the pocket watch, I'm setting it to 0. The other thing I did was to suppress or unsuppress the 6 and the 9 accordingly. So that's how, at the top level, I've got this working. I can switch to pocket watch, a wristwatch edition. Now we've got the stem coming out the side, like that, 12, and the seconds are at the 9 o'clock position. And pocket watch is going to have seconds at the 6 o'clock position and the stem coming out the top. Really cool, really easy to do. You can see that the configuration tables are so simple and powerful in Onshape. I really don't know some of these things, how I would have had to approach it using other tools, but Onshape makes it extremely powerful that way. All right, that is where I've got up to. I think that's the main. I've shown you everything that I wanted to show you in there. Shown you the cycloid gear custom feature. If you wanted to see the code, it's not that bad. It's just a pretty basic math here and some an additional function that does some trigonometry. Creates these, which I used for references for this. Next step is going to be finishing the balance here and putting in the power, the winding, the mainspring, the barrel, and the setting mechanism. The setting mechanism is a little bit of a trick. There's a few other things that go on this side, as you know from before, but let's not get too worried about that yet. I've done it before. This time it's going to be nicely parametric, and I will look forward to updating you on the success of that in the future.